Hello everyone! Today we have an electronics video for you. Today we're going to talk about Ohm's law and the power law, as well as answer a few basic questions of why this information is important and why I care about it. So if you do like this content, please do hit that like button. It lets me know that you enjoy these electronic videos and that I probably should keep making them. And then also, if you enjoyed all of the content on the channel, or you're just feeling charitable and you want to help the channel out, please do consider hitting that subscribe button. All right, so now with all the YouTube marketing stuff out of the way, let's actually get into it. Ohm's law is V equals I times R, which means voltage equals current times resistance. You'll remember in the last video we talked about overly simplified electricity for electronics, and in that video we discussed how the two things that you pretty much care about is voltage and current. We're going to add one more thing, and that's resistance. So whenever electricity is flowing, there will be resistance. Unless, of course, you have a superconductor. But we won't really get into that since those are sort of hard to make. Even your wires, which are conductors, will have a little bit of resistance in them. And then obviously insulators, there's a huge amount of resistance in them. So, and that's the point, so you don't shock yourself when you touch a wire. You have an insulator on there to protect you from it. So you might be wondering, why is voltage important? Well, voltage is important for a number of things, and in regards to this channel, which is basically a programming channel, we're going to be dealing with it in analog computers. Now, in digital computers, you take bits and bytes and you can add them together using circuitry to take different numbers and add them and get another binary number, which means that you've added, or you can multiply and you can divide and do all those fun sorts of things. However, with analog computers, specifically electro-analog computers, because yes, there are mechanical ones, we will not get into those, but, or at least in this series we won't. In the electrical variety, what voltage tells you is the answer to your problem. So let's say that you feed 10 volts in and you run it through a divider circuit and you want to divide it by 2, and it will spit 5 volts out for you. It just performed the math for you, basically at the speed of light, which is pretty cool stuff. So obviously we're going to be getting more into analog circuits here, and I do look forward to seeing you in those videos as well, but that is why voltage is important. And then talking about amperage, often your batteries are going to be measured in milliamp hours, and you don't want your battery to go dead almost instantly. So the less amperage you use, it will, well, for one, create less heat and consume less power, which we'll get into very soon, but also your battery will last longer. All right, I think we covered these three questions basically. Resistance obviously is the resistance of that flow of that amperage. Now we can actually see that in this circuit. If I close this one and let's hit run, you can see how fast these little dots are moving. And if you remember how fast they're going, you can see that they slowed down to about half the speed, since this is 2000 ohms and this one is 1000 ohm. Now while I'm at it, to make the math easier, we're going to keep this at 10 volts. And let's just run through or walk through an example problem here. We know that our voltage is 10 volts. We don't know our current yet, that's what we're going to figure out, but we do know that our resistance is 1000 ohms, which is the omega symbol. I don't have an omega key on my keyboard, I am not Greek. So we will just spell it out. So if we divide 1000 from each side, what will that give us? Well, let's see here. We should end up with 10V divided by 1000 ohms equals I. And if we simplify that into decimals rather than fractions, we will end up with 0.01 amps, which is A, and that happens to equal 10 milliamps. Hopefully you're familiar with the metric system and how if you move it over 3 decimal places, you end up with milli stuff, and if you move it the other way, you end up with kilo stuff and mega and giga. And if you're in computers, hopefully all these terms sound familiar with megabytes and kilobytes and gigabytes and all of that. That is the way that that works. So let's actually take a look at this and let's make sure our math is correct. If we close this circuit, we can see that indeed it says 10 milliamps, 10 volts, and we also are showing power at 100 milliwatts. Interesting. I don't remember adding power to this one, and generally that doesn't come on by itself. But, well, that's a good segue into the power law. So let's talk about that next. It is P equals I times E, which is easy to remember because it's pi. However, E and V happen to equal each other, so for sake of sanity, let's make it PIV instead. So obviously power equals our current times our voltage. So if we have 10 milliamps and we multiply it by 10 volts, what we're going to end up with is our 100 milliwatts. And we can just write that out real quick to show why that makes sense. 10 times 0.010 equals 0.1. And when we move that decimal place over 3 times, we end up with the number 100, which gives us our 100 milliwatts. Now, you might be thinking, what does the wattage mean in this case? You've probably heard about watts. If your house is hooked up to the grid, you've probably heard about kilowatt hours and things like that, how much electricity is used in an hour. In this specific case, we're talking about basically instantaneous, the amount of electricity being used, and it's being converted into heat. So in America here, generally heat is measured in BTUs, which are British thermal units. However, pretty much most of the rest of the world will measure it in wattage, which is why you might see things like a 5,000 watt heater or things like that. That is a way to measure heat and power and yeah, all that sort of good stuff. So that explains this circuit. Now let's open it up and let's ponder for a minute. Let's remove this. What's happening here? We can see that the current's moving half as fast, which would make sense because the resistance is doubled. So if we look at these equations, this 1,000 would turn into 2,000. And when we move it over to this side of the equation, it still would follow suit. And I believe, since this is basically the number 10, it would be halved. So we're going to end up with 0.05 amps, which is 5 milliamps. And our power consumption should also go down to 0.05, which is going to be 50 milliwatts. So let's see if we were correct in our math. We can see here that indeed we have a 10 volt drop. We are indeed allowing 5 milliamps through that resistor, and it is consuming 50 milliwatts of heat. So really that boils down to all of it. I guess kind of the neat thing that you can see here is how we were able to control the amperage by changing the resistance. We have, with resistors, a lot of capabilities of setting these values to whatever we want. So that allows us to control the amperage. And that is basically Ohm's law. The biggest takeaway I have for you is that voltage, current, and resistance are all related to one another. That is all that I do have for you in this video, and I do look forward to seeing you in future videos, and continue playing around with those circuits because there's always something more to learn and it's always a lot of fun.